Nolan, he's talking about you. All right, Jay. Oh, come on. JWDPJ. We're going to do a little writing and drawing here inside. Oh, you're a donkey. That's how sliding board works. JWDPJ. All right. Start that up. And I'll show you what I'm cooking with here. Let's clear all data. All right. So this little black box here acts kind of like the spring scales. Okay. So let me zero it here. And if I hang a kilogram from it, we see it reads 10 newtons. Okay. So that's good. All right. What I'm going to do is pull on this string here, okay, and then I've started doing a little bit of toy making at home for my children. So this is a train set that I made for my daughter Cora. I'm not really that good at it yet, but I mean, it's the first attempt. I think she'll like it, so hopefully we'll find out. But what I'm going to do is apply a little bit of force to that thing. And okay, so you see I'm able to apply a pretty constant amount of force to this thing, so I'm very skillful. And I definitely don't need the graph to be going that high. Let's go with 10. Okay, so you can see it's just under 4 newtons of force that I was applying. What I'd like you to do in the Pear Deck is go ahead and draw a free body diagram, not for the block, draw a free body diagram for the system. Okay, so think of that as the system. What would the free body diagram look like? And again, there are text tools and you have font size control, so rather than trying to scribble feeler dealer by hand, just hit the easy button. All right, and based on what I'm seeing, I'm going to invite you to talk to your neighbor a little bit here. I'd like you to draw the free body diagram for the system. Keep in mind when I'm pulling it like this. So what does that tell you, or what models are appropriate for this situation? Okay, so be mindful of that in your diagramming there. Any arrows that you perceive to be of the same length, make sure you're clearly indicating that with tick marks. So these are two examples that I'm seeing in there. I need you to consider these with your neighbor. And think about it in comparison to what you have drawn for your diagram. You make a strong case for either one of those. Okay, so given what those two diagrams are saying, given that when you're observing it, okay, during the period of interest, I'm pulling it like this. Okay, so what should that tell you about the diagram? Ooh, I need to grab. Maybe this will help you out. All right. So I'm going to collect that again. Eventually. Okay. Wowzers. Okay. So when you look at the velocity graph, the force graph, think about what model should apply here and go ahead and make any revisions to your diagram that you perceive to be necessary. Okay. And then I guess also take a visit with your neighbor there. The silence is deafening. Ah, there we go. Now you're picking up on it. Sorry, I should have the motion detector from the get-go. And I could ask you the model question as well, which models apply, but I can kind of tell now by what you're drawing that you're there with it. All right. So ooh, that's intense. So now if you look at what I'm seeing on my end, it looks like most people have decided clearly that there's as much forward force as backwards force here. These forces are balanced because the thing's moving at a constant velocity. Okay. So, ooh, and they've even got the amount here with this one. So you've got smoosh poosh, up, train, comma, counter, gravity down, train, comma, earth. I like what you're calling it, train, right? That's the system. This tension force, train, comma, me, and then an equal amount of friction in the opposite direction, train, comma, counter. Okay. That looks to be fairly universal. Gosh darn it. Fairly universal. Okay. If we scroll through these. Okay. So again, if you're including an FU here, what would we expect to see on this velocity graph if we were going to have an FU in that diagram? Well, what would have to happen here? Have to be either increasing or decreasing in velocity. We don't see that happening. So we're going to go ahead and understand that to mean that the models here are CVPM and therefore BFPM. All right. So here's my question to you, and I'm going to throw this back onto the pair deck. There's that. Oop. So because it's BFPM, because the velocity is constant, the tension and the friction have the same value. Okay? So although this thing is actually reading the tension force, it serves to also give us an understanding about the frictional force. What I'd like to hear from you about here, what are some things we could change about this situation that would increase, or I shouldn't say increase, that would change the amount of friction, increase or decrease it, okay? So have a quick think about that with your neighbor, and if you could just type in 2 or 3 things that you think have the potential to change the amount of friction that the system is experiencing. So again, what I'm asking you for are some things that you think we could change that have the potential to change the amount of frictional force. Okay, some of you are still typing, but we can look through some of this stuff. We see change the surface area, change the slope of the incline, change the length of the train, harder, change the weight of the train, change the force Harding applies, put it on an incline, place it on a frictionless surface. Okay, that would probably change the amount of friction. Put the train on ice. Okay, where are we going to find ice at this time of year? Surface area, oh wow. What movie is that script from? Use a different surface. Rougher likely means more friction. Incline will lessen the effect of FG. Decrease the downhill, increase uphill friction, surface tension. Surface area of the train touching the table. So if I kind of summarize these things, we've got surface area. Ooh, where's the... Yeah, check this out. Oh, yeah. Ha, ha, ha. How cool was that, huh? Surface area. Surface type. Where was that at? Ha, ha, ha. Oops. Nice. All right. Surface area, surface type. FG/mass. What else were you find people saying? Surface area, surface type. Incline, angled surface. Okay. I don't think I saw this anywhere. But some people talk about having me pull harder. What about if I pull faster? What effect will that have on the amount of friction? Okay. I think that will be more friction or less friction. So anyways, that's kind of our list to work off of here. I'm going to say the constant velocity at which I'm pulling. Okay, surface area, that's pretty easy. I can just flip this thing on edge. And what did I just do to the surface area? Decreased it, right? Pretty massively so. And let's go back over to the graph. And I'm going to store this sucker. And then all right, how did I do on the velocity? Is that pretty close to the same velocity as before? Right, I didn't change too many things. What do you notice about the amount of friction? Same. So we made the surface area less, but we're still seeing the same friction. Can you run that by your neighbor quick? What is some sort of explanation for that? Why did decreasing the surface area not decrease or increase the friction? Ooh, in fact, I can get nutty with it. Like this. Now clearly there's less. I got too cocky, didn't I? Flew too close to the sun. So we'll just stick with what we had before, which was the same. Yeah, what's up with that? Certainly changing the surface area by a significant amount, but not seeing a significant change in the amount of friction. It is kind of tough for the motion sensor to pick it up. There we go. So yeah. So that's going to get the mastering red X of shame there for surface area. Okay. What about surface type? Surface type. So I've got the counter. Unfortunately, that's kind of like the predominant surface type in the room. I got this thing here, okay? I'm going to have to shrink the train down a little bit. So, would you feel this fine cloth? How would you describe it? Luxurious, sure, but also very smooth, okay? So if I lay this smooth cloth on the table, what do you think that's going to do to the amount of friction you see? We're going to bite me. All right, I'm going over here and check it out. What do you think? Compared to the trial where we changed the surface area, are those identical? We went from like 4.8 to like 5.2. Okay. I got this option available to us as well. Oops, that's not really going to work for the motion detector. Okay, I think that's a clearly different amount of friction involved here. Okay, so it seems that the type of surface, and this is probably not counterintuitive, the type of surface involved matters. So let's give that the green check mark. That darn ink to text thing made that kind of small. FG and mass. Okay, so if you think about the free body diagram that you had going there, you've got the train. I don't want that right there, do I? You've got the train. You've got gravity down like that, train, comma, earth. You've got smoosh poosh up like that, train, comma, surface. You've got tension in the forward direction, train, comma, Harding. And you've got friction like that, train, comma, surface. And we understand that to be the case and that to be the case. If I change the mass, what all changes in this diagram? Run that by your neighbor really quick. If I change the mass of this thing, what other impacts is that going to have? So let's check it out, right? Like if I take these blocks off, now this is less massive. Let's give it a run here. That changed the amount of friction? Okay, definitely. But changing the mass did what to this free body diagram? What's one thing it changed? Stassel? Gravity. Gravity would be less, yeah? We decrease the mass. Okay? Anything else that changed here? FSP would also be less. Okay? Or if I do this, if I put more stuff on here, let's give that a whirl. Oh. Okay, so yeah, clearly more friction, but keep in mind, we made the mass bigger, but consequently that's going to mean bigger gravitational force, which consequently means bigger smoosh poosh force. So riddle me this, Batman. Can you come up with a way that we can just change one thing without changing three things? The problem here was we changed three things. What's a way of doing this where we say maybe just change the smoosh poosh without changing mass or gravity? Run that by your neighbor quick. How can we make that happen? Talk to your neighbor, talk to your neighbor. Is that possible? All right, so run that by Pear Deck. What do you got for us? How could we change, say, smoosh poosh without changing mass or gravity? Oh, fifth hour, you amuse me. All right, so we take a peek at what some of you clever folks are saying here. Incline, pull upwards on the no longer a train. Add an incline, incline, decline, incline. Pull at an angle, angle of incline. Change the angle of the surface. Change the direction of the FT. Okay, drop it. Fair enough. I'll tell you this, unfortunately, the table is rigidly attached to the floor, so I can't really do much about that right now, but we are aware of how changing the angle of the surface would affect the smoosh poosh, okay? And then cleverly, I incepted this by having you work on a sweaty man box problem the other day. We also know that smoosh poosh can be affected by tension at angles. So what I'm going to attempt to do here is pull at an angle of, say, oh gosh, I'm going to aim for right around 60 degrees, okay? Now, unfortunately, in order to accomplish that, I'm going to have to zero this thing at an angle of 60 degrees. Let's see if I can pull that off. Yeah. Ooh, and I need to store that latest run. Where's my control L? Okay, so we have our baseline value when I just pull it straight across, but then I'm going to try to pull this thing at an angle of 60 degrees. That was a bad idea. All right, what do we do? We don't know. What do we know? It's more force. So this is the issue. Now the tension doesn't equal the friction, okay? Because the tension's now at an angle of 60 degrees. So with our diagram, I don't think I can. Oh, buddy, what's going on here? With our diagram, I don't think I can just change the angle of the arrow. I think I have to redraw it if this thing decides to work. There we go. So I'm putting this angle, or this arrow, I should say, at an angle of 60 degrees. Okay. So imagine what that does to our diagram here. So we do this. So I pull that out like this. We go here. Hello, arrow. There we go. Oh, crap. Are the forces no longer balanced? Or are they balanced? Should the forces balance? Chai says yes. Why? Well, if we go back and look at the graphs here, what's true of the motion of this thing-ish? Pretty CDPM. So it should still be BFPM. And again, this kind of goes back to the sweaty man box problem. The thing that I need to understand about this is guess at my trig better. There we go. The thing that I need to understand about this is that the smoosh poosh is going to be a little bit less because this tension is at an angle. All right, we'll have to call that close enough for government work. Boop. Right? So that's the whole idea of changing that angle changes the smoosh poosh, but does not change FG. So this is 60 degrees. If we go over here, it's right around, oh my gosh. Nope, that's not what I want. Right around 21 newtons, okay? As compared to that, when I pulled straight on, was 15 newtons, okay? So have that in mind, that this 15 newtons is when the tension and the friction were equal. Right now I've got 21 newtons of tension. But if that angle is 60 degrees, what is the friction? So we're going to do this thing here where we take that 21 newtons at 60 degrees and decompose it into a right triangle. This is probably some trig we're already doing with these types of things. So this arrow right here, this horizontal leg of this, if it's 21 newtons and it's 60 degrees, what is this? 10.5 newtons. And then this is 10.5 root 3. Okay, so the smoosh poosh is less by 10.5 root 3 newtons, whatever the hell that is. Okay, but the friction now is 10.5. It's 10.5. When I pulled straight on, it was 15 newtons. But now that we're pulling at an upward angle and reducing the smoosh poosh, now the friction is only 10.5 newtons. So we didn't change the gravity, but what we did change was the smoosh poosh, and saw, in fact, that has an effect on the friction. So where's the green? Boop. Check mark. Okay. That kind of ties into the angle of the surface. Okay, because that's going to affect the smoosh poosh. That's what we have going on there. Okay. Velocity. Let's go back and take a look at that quick. That wasn't one any of you had mentioned, but I had it. So let's get rid of latest run. Okay. So the dark blue is our baseline, our reference here. Okay. And it's like 15 newtons. I'm going to try pulling at a different constant velocity. I'm going to try pulling a little bit faster than I did before. Let's see what happens here. I forgot to zero this sucker. All right. All right. Faster? Okay, by at least a factor of 2, it's faster. Friction amount? It's pretty similar. Okay. Let's see if I can go faster yet. Kind of got kind of wonky there, huh? That was definitely faster, though. Let me get a little screwy with it. Okay, so we're like a factor of 3 faster, but if you look here in the main, it's pretty similar in terms of the amount of frictional force that's involved. Okay, changing the velocity doesn't really do much to the friction. Okay, it's independent of how fast this thing is going here. So I'm going to red X that real quick. And really, it looks like the things that are affecting the amount of friction are the smoosh poosh and the type of surface. Okay. You kind of notice, though, this kind of topography over here. Okay, and I'm gonna clean this up a little bit so we can take a closer look at what's going on here. Data, clear all data. Okay. All right. Is there friction right now? What do you think? Run that by your neighbor. Was there friction involved there? All right, I'll show you what I did again. I did this. Okay, and so the Pear Deck is asking that. Is there friction involved here? How do you know? Yeah, let's see what our friends are saying over here on the Pear Deck. Yes, because a force applied must form three other forces. No, because the train did not move. Yes, the train didn't move despite tension, implying that tension is less than friction. Friction is what's preventing it from moving. Yes, because you were applying force on the system, but the system is not moving, ergo the force of friction. Otherwise, the forces would be unbalanced. On the horizontal axis, the train would move. So it kind of comes down to that. Where's my slide? Yeah, right? The free body diagram. What? So I'm pulling here. There's a tension. Let's listen. Is that A? Okay. There's tension here right now. But this thing's not moving. What models apply right now? Michael, it's right in front of you. What are you thinking? What models are applicable? CVPM, it's got a constant velocity of 0. Therefore, BFPM. So if this has got tension, there's an arrow pointing this way, FT, there must be something acting in opposition to keep this thing with a constant velocity of 0. Okay? So that's another thing I would ask you to note about the friction. Because was it constant? Not. It's varying in response to whatever I'm doing here. So if I have my free body diagram, it seems that, oh boy, that's a mess. Ooh, that's not what I wanted. That doesn't erase. Boop. All right. It seems that I've got arrow down, I've got arrow up. Those bounce. If I pull with just a little bit of tension, we get just a little bit of friction, okay? If I pull with a little more tension, it's still balancing. It's not changing its velocity at all. So if I pull with even more tension, I don't know why I'm labeling that one. If I pull with more tension, there's even more friction involved. So I need you to understand this, that while it's at rest, the tension force is variable, okay? So understand that from the appearance of this graph. The velocity is 0 this whole time. Whatever I'm increasing the tension to, the friction has to match it, otherwise the velocity would change. So for objects at rest, friction force is variable. FF varies, okay? It's easy to determine if I know what the other force is. That's how much friction there is. So I'm going to go back to this thing, and I'm going to put the motion detector. This time I'm going to attempt to get it into motion. So notice here initially I'm increasing the tension. I'm increasing the tension. Okay, and then right at the end there, it started moving. So if you look at, ooh, I can snip this. If you look at these graphs, why is it doing that? Give me the snip to, oh, new. Perfect. Well, that's tiny. If you look at the graph, think about what's going on here in terms of the free body diagram of this thing. So I'm going to give you 3 points in time. Can I draw on this thing? Yeah. Let's call this A. I'm going to call this B. And I'm going to call this C. Okay? And if you look at what's going on, on the velocity time graph below at that time, think about what's going on there in terms of forces, okay? So draw free body diagrams at the indicated spots. So that first dot at A, that second dot at B, and that last dot C. Let's keep things simple. We know gravity and smoosh poosh are not affected there. So have a go at the free body diagrams for A, B, and C. And again, I'll just kind of know, we know what's going on here in terms of gravity and smoosh poosh. Please use tick marks to indicate any arrows that you perceive to be at the same length. So I guess what I'm fishing for here, similarities and differences, A, B, and C. I try to be really deliberate about where I put those 3 points. That's why I'm asking you to put tick marks anywhere on these 3 arrows where you perceive the arrows to be of the same length. Okay, and so here's a couple of examples that are kind of picking up what I'm trying to put down there. Single tick marks here and here. I had A and C very deliberately set at the same amount of force. You have this position, though, where the force was greater. So here it is at rest. Here it is moving at a constant velocity with the same amount of friction. Okay. In between those points was this period of time where the friction force was even greater than it is now that the object's in motion, okay? And if you look on this graph, there's kind of a, I should pop over onto this thing. There's a point in time where this thing goes into motion. That happens right about here. And if I go up on the graph here, you can see that just prior to that, there was kind of a threshold. Okay, buddy, it's draw. I'm not sure that's how you spell threshold, but I'll try. There's like a threshold value. Okay, the friction increases to a point, but ultimately you reach a point that the friction can no longer match the tension. Now the thing goes into motion, and once it's in motion, so after this point in time, it's subject to a reduced amount of friction. Okay, so there's sort of a constant change in the amount as we move from A to B here. But then just after B, we reach a value of tension that the friction can't match. So this thing starts moving, and once it starts moving, it's subject to less friction. So what we're seeing here are two different types of friction. Over here, this is called static friction. Okay, and that happens when the velocity is 0. And over here we have kinetic friction when the velocity is non-zero. All right, we'll pick up with that tomorrow.